Here we are with the NIDAM learning module for control engineering. It consists of an actuator, a process, a plant which is a motor, and a sensor. We used it to create a digital control system. The other parts of the system are a few electronics. This is the power supply, a filter to generate a DC voltage from a PWM signal. This PWM signal comes out of a controller and it represents the control signal. Our controller is implemented in an arduino, which communicates serially to a visual interface built with labview. So we implemented 5 types of controllers, and we're going to show the system first in an open loop behavior. So we're going to set about 1500 RPMs, and we're going to send the command. 1500 RPMs, and this is how the system behaves. As we can see, we didn't reach the exact value, and if we introduce a disturbance, the set point falls because there is no control system. If we change to our first controller, which is an on-off controller, we see an oscillating behavior. This is because on-off controllers are not meant to be very precise. But if we introduce a disturbance, we can see that there is a sort of compensation. So the next controller is an on-off controller with hysteresis. The behavior is practically the same, but there is a threshold, so it takes longer to switch, and it still compensates a little bit with disturbance. Our next controller is a proportional, and as we see, we don't reach the set point because proportional controllers have that defect, but there is certain compensation. Our best 2 controllers are the next ones. Here we have the PI controller. As we see, it is slow, but it reaches the 1500 RPMs. And if we introduce a perturbation or disturbance, it slowly reaches back to the set point. And in the graphs, we can see the error going to 0 every time a disturbance is added or removed. The last type is a fuzzy logic controller, which works very well, just like the PI, but faster. We can see that when we add a disturbance, it goes back to the set point very quickly.